Right, now we have said that the problem with covariance is that while it tells us the direction of linear association between any two variables of our choice, it has the problem that it is sensitive to the scale of measurement and to the units of measurement. Now, so we want a measure which preserves the direction of association but eliminates these two problems of scale sensitivity and unit of measurement sensitivity. And that particular measure is called a correlation coefficient. Now, correlation, as I said, it measures the reliability of linear association of any two variables. In other words, we are looking at the linear association between education and wages, but we want to develop a measure that tells us how reliable that linear association is. Then correlation is the natural candidate. So from the table you see here, this is what we have as our original data. We calculated these deviations from the mean in our previous example. The only new thing now is that I have squared this deviation from the mean, which gives me this column with very large numbers, and I have squared this deviation from the mean for education, and it gives me these numbers here. Now, whenever you square deviations from the mean and you adjust them for the degrees of freedom, remembering that using this data we already calculated one sample statistic called the mean. So our degrees of freedom are the sample size minus 1, referring to the one that we have already calculated. So if we adjust, we have squared these, we add all of the 7 of them, we get this number here. This number here, if you are reading your book, you probably, let me just remove this part. If you are reading your book, you will come across something like this. So it is the sum of y minus y bar squared, okay? Now, if I adjust this for degrees of freedom, I divide by the sample size and I subtract 1 because I used the data to calculate the mean. This number here is called a variance, okay? It is telling us the dissipation of the data because this is measuring how far the data is from the mean. So squaring that deviation tells us the extent to which observations are dissipated or far removed or closer to their mean, okay? So if we take the square root of this, we get what is called standard deviation, okay? It is the square root of that, y minus y bar squared over n minus 1, okay? So for x, you do the same. Now, therefore, what it means is, if our covariance, as we calculated earlier, is equal to the sum of y minus its mean by x minus its mean, and all this is divided by n minus 1, okay? All this is divided by n minus 1. If we want to eliminate the units of measurement, which is our rand dollars. Okay? What we have to do is we have to divide this particular number here by the standard deviation of wages and the standard deviation of education, which means we are just saying all this divided by standard deviation of wages by standard deviation of education. This particular number you have here, which is your covariance over the product of the two standard deviations, is what we call the correlation coefficient. Okay? And this particular number lies between -1 and 1. Okay? Let's call this, let's give it a name P less than 1. It lies between -1 and 1. If it is exactly -1, it means that education and wages perfectly move in opposite directions, 1 for 1. If education increases, wages go down, right? Now, if it is 1, it means they perfectly move together. But in reality, it's never around these numbers. It's somewhere in between. Let's say you find it to be 0.8. You can see that it's a high correlation coefficient, which means the linear association between education and wages is highly reliable. Remember, correlation is about reliability. They are strongly and reliably linearly associated. If it is, let's say, -0.9, it is also a high number anyway. So it means it's highly reliable, but it's a negative relationship. Do you see that? So now, given that we have calculated the components of our thing, we now want to find the correlation coefficient, which we said is equal to the covariance of wage education divided by the standard deviation of wage times standard deviation of education. This should be equal to, we calculated our covariance the other time, I think it was 309.52. We are dividing this number by this, which is your standard deviation. This is your standard deviation for education, and this is your standard deviation for wages. So divided by 10,541.3 times 6.16. What do we get? Let me just do that very quickly. It's 59,309.52 divided by 10,541.3 times 6.16. We get 0. My answer is gone. So 59,309.52 divided by 10,541.3 times 6.16. We get 0.913. This is a very strong positive linear association. In other words, we are saying In our data, we have seen that as you move or as you increase the number of years of schooling from 0 to about 18 when you get to masters, your earnings are going up. That linear relationship which shows that as this one goes up, that one goes up, is very reliable. A very strong linear association of 0.913. So what you see here is that there is a relationship between correlation and covariance. Isn't that wonderful? Very wonderful. Now it is from these two relationships that we can easily get also, we can easily measure the effect of education on wages using these two. That is why I was saying if you know covariance and your correlation, you can get a measure of the effect of education on earnings and so forth. But for now, let me stop here. What matters is that we found the variance of wages, and we got the standard deviation, the variance of education, and the standard deviation. Using these two standard deviations, we adjusted the covariance to get a measure which is not sensitive to units of measurement, because this number here it's a pure number. It doesn't have dollars, rands, or years. It's just a pure number like 1. So it doesn't have units of measurement. Secondly, this number doesn't matter if I had written my wages in thousands, removing the thousand and just writing 0.5, 3, 8, 10, 18.5, 22.5, 29, instead of adding the 3 zeros, I would still get this number, which means it's not sensitive to the scale of measurement. That's enough for today. When we meet again, I'll begin to talk about regression analysis.